Hello everyone and welcome. Welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences in order to motivate and promote scientific thought and its creation, as well as to minimize the negative impact on it of the situation with COVID-19 outbreak in the world. This evening, we have another wonderful episode of our Quantum Science and Technology Seminar Series. And I have the honor of introducing our speaker, a world-class expert in the field of quantum science and technology. Professor Igor Lesanovsky from the University of Tübingen in Germany, as well as from the University of Nottingham in United Kingdom. He's going to give a great talk about exploring non-equilibrium physics with synthetic quantum systems. Professor Igor Lesanovsky studies quantum physics, focusing on a wider range of topics, such as strongly correlated spin systems, relaxation and thermalization of closed quantum systems, trapping and manipulation of highly excited Rydberg atoms, collective phenomena in ultra-cold atomic gases, creation of non-classical state of light and matter, quantum information with atoms and trapped ions, and non-equilibrium in quantum open systems. Igor Lesanovsky is a full professor at the University of Tübingen in Germany, as well as a professor at the Department of Physics of Nottingham University. After receiving in 2006 his PhD from the University of Heidelberg in Germany, at the same year he started postdoctoral work at the Institute of Electronic Structure and Laser in Heraklion, Greece. And then he did postdoctoral work at the University of Innsbruck in Austria between 2007 and 2009. In 2009, he joined the Department of Physics of Nottingham University as a lecturer in physics, where later he became professor of physics in 2013. Since September 2019, he is also a full professor for theoretical atomic physics and synthetic quantum systems at the University of Tübingen in Germany. Professor Igor Lesanovsky is the recipient of 2014 Maxwell Medal and Prize for his world-leading research in the world of quantum matter. With this, I want to thank once again Professor Igor Lesanovsky for joining us for this seminar. We are really honored and looking forward to it. Igor, you're welcome to begin your talk.
Alikram, thank you very much for this ultra kind introduction. It's of course a pleasure to be here and to be able to give this presentation to all of you, despite the situation we are all facing, which hopefully will be over and managed soon. As was said in the introduction, I'm going to talk about non-equilibrium physics and how it can be explored with synthetic quantum systems. Details will follow. Just to tell you a little bit about the current situation I am in. So I was spending 10 years of my life in the UK at the University of Nottingham, where I still have close ties to, and also part of the work that I'm going to talk about here is carried out by a postdoc, Edward Gilman, who's still based at Nottingham University. And then in 2019, I got an offer from University of Tübingen, where I moved to in Germany. And I'm in the process still of building my group. Obviously, the situation is not that easy at the moment, but I think we are managing reasonably well. And the research that I'm going to present here is in large part also carried forward by one of my excellent postdocs, who is called Federico Carollo. So this brings me to the outline of the talk, and what can I say? Don't expect too many answers. Yeah, so it's more about like showcasing possibilities of research ideas that connect to recent advances in also the experimental domain of quantum physics with many-body systems. Yeah, and the attempt that I'm going to, so to say, advertise here is to connect these advances in the realm of controlling quantum systems with interesting dynamical phenomena that can be observed in the framework of so-called cellular automata. And I will discuss all these words that I just dropped in some detail and hopefully give you a flavor of the kind of research that we are interested in. And I will actually also connect this somewhat to the current situation where we are facing this epidemic spreading of a virus, which in itself is, of course, also a non-equilibrium phenomenon. So let me just briefly go through this outline here. So synthetic quantum systems, this is what I'm working on. And what this means is, well, quantum systems that are created in an artificial way, let's say, by atoms that are arranged in regular lattice structures. And these atoms can, of course, be also manipulated internally. They can be excited from the electronic ground state to electronically high-lying states, so-called Rydberg states, where they strongly interact. And with this, you are able to create and investigate a whole range of non-equilibrium phenomena, as I hopefully will be able to convince you about. So then after setting the stage, I will jump into the realm of classical and quantum non-equilibrium processes. Obviously, time is limited, so I'm trying to convey a message concerning why this is interesting and relevant and complicated and also intriguing, because there are obviously some open questions that needs answering. And in the next step, I will then advertise so-called open quantum cellular automata as a kind of interesting setting that A, can be realized on these Rydberg quantum simulators, and B, allows to study and analyze quantum non-equilibrium dynamics in a very clean and controlled fashion. So I will tell you what precisely I mean by quantum cellular automata, because this is certainly not a term that is unambiguous. I will tell you that these systems allow to implement and study non-equilibrium phase transitions, and that they also permit, and this is why they are interesting in my opinion, the introduction of non-classical correlations in a very controlled fashion, and you are able to really distinguish between classical and non-classical effects and how they impact on the non-equilibrium behavior of many-body quantum systems. Good. Okay, so synthetic quantum systems in a nutshell. So I think the good starting point for just showing you what this is all about is this picture that is by now already a few years old, was taken by the group of Antoine Brevet and Palaiseau near Paris. And what you see here is, well, football. Well, the Euro Cup is starting soon, so good connection there. And this football is actually composed of individual atoms that are held in traps, in optical traps. And you see every green point that you see here represents a trap that contains an atom. So what I want to convince you of here is that it is now possible to create really atom by atom arrangements of many-body particle systems in an almost arbitrary fashion. So, and as I said, each of these green dots you can think of representing an atom that, in a very simplified fashion, please take into account that I'm a theorist. I don't want to be concerned now with too many details concerning the electronic structure of the atoms we are dealing with. For the purpose of this talk, it will be sufficient to understand an atom from the perspective of a two-level system where we have a ground state, and in this ground state, the electron is close to the nucleus, and they have a second state, which we call the Rydberg state, because it has a strong resemblance with excited states of a hydrogen atom, whose energies are, of course, given by the so-called Rydberg series. And in these Rydberg states, the electron is far away from this nucleus, encircling it on a high-lying orbit. And you see already from this picture that these atomic states give rise to some kind of interaction if there's more than one atom present, because you see already by this picture here that these this atom forms an electric dipole with a positive and a negative charge, and consequently, if you now place a second atom nearby that is also excited to a Rydberg state, these dipoles will start interacting. It's a strong and measurable effect that competes, for instance, with the laser excitation. There's lots to be said about this as a basis for quantum information processing and so on and so forth. So this is a really interesting field in its own right. But the bottom line here is that these atoms on these Rydberg quantum simulators allow to engineer spin systems that essentially have more or less arbitrary interaction and geometry. Obviously, this two-level description of our atom lends itself very nicely to a description in terms of an artificial spin. And just, as a warning is maybe said too much, so in this talk I will really switch between the notion of excited atom, ground state atom, or spin down, spin up state. You can really see somehow these terms as completely synonymous. The down state would correspond to an atomic ground state, and the Rydberg state would correspond to this up state of a fictitious spin, which is of course represented by a set of Pauli operators. And you know this from your quantum mechanics lectures. So now with all this, you have a whole toolbox at your disposal where you can essentially create Hamiltonians of that type here. I don't want to go too much into detail, but what you can do is you can create single body Hamiltonians which resemble the interaction of this fictitious spin with external fields whose shape and structure you can control. And more interestingly, the fact that high-lying Rydberg states interact, it allows you to create effective spin-spin interactions that are binary and would look like that, with a coefficient matrix J, whose shape you can control and whose shape obviously also is determined by the properties of the atomic states. And on top of that, you can, of course, also have dissipative processes that are not reversible or coherent like the quantum mechanical processes. These are, for instance, dephasing. So this is just erasing quantum superpositions, a process, or decay. I mean, this is certainly something you're familiar with when you have an atom that is brought into a highly excited state. It will decay over time and then will be found at long times in its ground state. And this is an example for a dissipative process. And now you can even let those two processes here, coherent dynamics and dissipative processes, compete. And this opens up a whole, let's say, toolbox, I said this word before, for studying quantum non-equilibrium phenomena. And just here give a non-exhaustive list that what has been done in the context of these Rydberg states. Certainly phase transitions have been observed, topological phases, then these quantum scars, time crystals, you use them for quantum information, quantum engines, quantum annealing. It's a fantastic system to work with. And I hope if you agree with me that this platform appears to have really a lot of potential for doing interesting physics and pushing the field forward. So in this talk, I want to focus on a particular aspect which concerns the non-equilibrium processes. And unfortunately, we are all subject to such a non-equilibrium process right now, which is, unfortunately, this COVID pandemic. And just to write down a very simple model of this pandemic, obviously you can refine it. You can say, well, let's consider a system that is composed of sites, and these sites can either be healthy or infected. So white is healthy, black is infected. And now you have two processes that can compete. Obviously, infected site can become healthy. Yeah, it's healing. So this is hopefully the outcome that is dominant. And if you have an infected site or an infected human being, you can infect one of your neighbors, and this is this process here. So, and this pandemic is driven by the competition between healing and infection. So I don't want to drop many equations also here at this introductory part of the talk. I just want to tell you that, of course, one can now write down an equation for this process, which takes into account the healing that takes place at a certain rate and the infection that takes place at a certain rate. And one describes this dynamical process by a first order differential equation, which describes the evolution of the state of the system, which for our quantum problems that we are interested in is given by the density matrix rho, and the evolution, this competition between healing and infection, is then encoded in some form in this linear operator L, the so-called master operator. So now you need also, in order to be able to study the physics, you need to agree on what property you actually want to investigate. And a good, let's say, order parameter in this regard is the density of infected sites, because it signals or gives you within one number in information of where you are with respect to this pandemic. And this order parameter is just the density of infected sites that you can, by quantum mechanical rules, just calculate as the trace of the density matrix times the corresponding operator. And then another quantity you're of course interested in is the stationary state. So the state which you will reach after very long times. And also here in the stationary state, you can define some density of infected sites just by using this quantum mechanical formula. And now if you do this, you find the following. You find that at very long times, you have two possible outcomes for the density of infected sites. So if the infection rate is high, you get a so-called active phase, where you always have a certain number of infected sites / humans. This is obviously not where we want to be. This is the phase in which this virus would be endemic. On the other hand, you have an inactive phase when the healing rate is sufficiently large, or conversely, the infection rate is sufficiently low. Then you have an inactive phase, and then in this inactive phase, the virus is eradicated because there are no infected sites any longer. And you see, as soon as you have a situation where all sites are healthy, it's no longer possible to have this infection process, because you need at least one infected site in order to trigger further infection processes. So this is a non-equilibrium phase transition, and it happens at a particular value of this infection rate. And this is now kind of statistical physics in a nutshell. So in order to analyze this phase transition, you typically focus at the vicinity of the so-called critical point here, where you go between the inactive phase and the active phase when you are changing this infection rate by a small amount. And if you think about your statistical physics class, then you know that in the vicinity of this phase transition point, the order parameter follows a characteristic power law as a function of this infection rate. And this is what I plotted here. So the density of infected sites goes at lambda minus the critical lambda. So lambda is the infection rate to the power of beta, which is a so-called critical exponent. Or what you can also do is you can tune yourself to the critical point and just start from a ensemble of infected sites and see how the number of infected sites drops over time, because at the critical point it has to go to 0. And what you will find is that there's an algebraic decay, so a power law decay with a characteristic exponent delta. And those two exponents can be used to characterize the system, and in particular allows you to understand what kind of universality class this system belongs to. So this is all known, and the classical process, as I said, in some more complicated version, of course, is happening right now. But now let's come to the stuff that we are interested in. We are not really, well, interested we are, but we are looking for problems that are difficult, and this is why we are not necessarily interested anymore in this classical process, because this is well understood and solved. But what we want to do is we want to think a little bit differently and say, well, let's just make up a non-equilibrium process. And one could ask a question that is, of course, completely hypothetical, but nevertheless can be implemented in the system. And the question would be, what if this infection process was actually quantum? If we now said we had these two sites, one infected, one healthy, and now you have not a rate connecting this state infected healthy to the state infected, as I showed you before, but you had a coherent process which could bring this system of infected and healthy site into a superposition between a state where the system is infected and healthy, or both sides are infected. So now, obviously the physics is different, because the classical process is described by a rate equation, and the quantum process is described by a quantum master equation. And already to see that there's a difference without really doing any calculation, you can run some trajectories. You can start with a single infected site, and you can see how this infection spreads now over time through space. Yeah, you see, I mean, here you start at time equals 0 with an infected site, and you infect the neighbors and so on and so forth. And this whole virus is spreading over the entire population. This is the classical situation where a site can either be infected or healthy. But in the quantum world, it would be possible to also have superpositions. So a site can be healthy and infected at the same time. And this is what you see here. It's exactly the same situation, but now with this coherent process. And you see, again, you start from a single site. You still have the spreading, but you see it looks completely different. It looks different in the sense that you also see now that you have these intermediate shades, so that these sites are no longer either healthy or infected, but you can have this kind of intermediate value that is just coming from the quantum nature. So also this quantum process, it turns out, has actually a phase transition between this healthy state and the active state where the virus is endemic. But the interesting thing is now, if you look at this more closely, you find actually that these exponents, beta and delta, are different for this quantum process. Yeah? Just if you are interested in this, or if you, let's say, are from the field, I just throw the names at you. Yeah, you find that the classical process is in a universality class, which is called directed percolation. And the quantum process appears to be, I mean, this is not entirely settled, in a universality class that is called tricritical directed percolation. So these beta and delta exponents are different. Also, what's interesting is that if you now look at this quantum process in 1D, as I said, it turns out to be in the tricritical directed percolation universality class, but of the two-dimensional version of this universality class. So you somehow extend the dimension here from 1 to 2, which is also something which is weird. I mean, it's not unheard of in equilibrium statistical physics that there's this notion of dimensional reduction, where you can relate a d-dimensional quantum problem to a d-1 dimensional, a d-dimensional classical problem to a d-1 dimensional quantum problem. But here, this connection is not easily established, because in these non-equilibrium processes, there's no notion of, for instance, partition function, where you could perform such manipulations that would allow you to show this direct connection, or this dimensional reduction that is known from equilibrium statistical physics. So this is somehow the punchline why I think this is interesting. So you can create artificial processes that are not realized necessarily in nature. I mean, who knows, maybe this is realized somewhere. But here we just say, well, we could in principle realize this on this Rydberg quantum simulators. Now, let's move on, and let's talk a little bit about how we can now construct a platform on which we can, in a systematic fashion, analyze the role of classical and quantum effects. And this leads us to the notion of quantum cellular automata, which I will show you in a second, are actually quite clean systems to study, because you have an evolution in discrete time over a discrete lattice. So all these finite size effects that could, for instance, emerge in simulations are well under control. And I will also show you that they allow in a very systematic way to introduce actually quantum effects and allow you to investigate the impact, and potentially also allow you to understand why, for instance, quantum processes feature different universality classes compared to the connected classical processes. And the framework in which we want to investigate this are so-called, quotes, in parentheses, open quantum cellular automata. This term is heavily, let's say, overloaded because there are many different things that are called quantum cellular automata that are actually completely different. It started here in '88, more than 30 years ago. Also here by a not completely unknown person, Anton Zeilinger, who looked at unitary evolution, closed quantum system evolution, and rephrasing this in terms of cellular automata. You have here quantum cellular automata that are in fact classical. Yeah, so it's something that has been investigated in solid state devices. And yeah, you have all, it's now recently popping up again. Here's a review over quantum cellular automata. And the interesting thing is that everything that is published here also recently is actually different to what I'm going to talk about now, which this is why I'm putting this word open in front of this. So what do I mean precisely? And let me come back to these Rydberg quantum simulators and let me tell you a little bit more in detail how we envisage this open quantum cellular automaton setting for the exploration of non-equilibrium many-body physics. So this is a picture again taken from the Palaiseau group. It's also pretty old by now, but what it shows you is a lattice, a 2D lattice of atoms that can be in the ground state or brought to the Rydberg state. And now there are a number of labs in the world who actually investigate this. Of course, there's the Lukin group, there's the group by Christian Groß here in Tübingen as well. You have Bloch, you have the Ahn group in South Korea, Max Saffmann, you have in Wisconsin. And there are many, many groups who have now realized such kind of system and are starting to play with it. So what we can say now, in order to implement our non-equilibrium process, what we do is we just take this two-dimensional spatial lattice and say, well, one direction we regard as time and one direction we regard as space. So, and now what we do is we prepare an initial state here at the top of this lattice and we propagate it through to the bottom of this lattice. So it's like in an old TV screen, yeah, and like this. I will show you on the next slide also in more detail how this works. What we do is we create a quantum state, yeah, on this two-dimensional lattice that allows to access the full temporal information, because we can also kind of go back in time because the state is living in this two-dimensional lattice. So where we interpret one direction as the time axis, but still we can look at the present, we can look at, but we can at the same time look at the past, because obviously the state is not gone, even though we are just moving down, down, down in the time direction. And this is kind of interesting. It allows somehow to really investigate the whole space-time structure of this non-equilibrium process at a glance. Good. Now, how does this work? So in practice, yeah. And the key to this idea are so-called quantum gates. And I told you already at the beginning, without really saying a lot of detail, that these Rydberg systems are actually extremely well suited to present to implement such quantum gates. And it has been shown now many times that they can actually really do this with a very high fidelity. And what we are going to do here for the purpose of this cellular automaton construction is to say, well, we consider gates that involve three atoms, yeah, that sit on this triangle. So this is kind of the triangle enclosing these three atoms on, let's say, in our real experiment. Here, this is how it looks in theory. And what we say is, well, these two atoms here at the base of the triangle are the so-called control atoms, and this one atom here, which is turned at the tip of the triangle, we refer to as target atom. And now what we do is we perform conditional operations on this target atom, and these operations are conditioned on the state of the control atom. So I just show you this picture says more than 1,000 words how this works. So suppose there's the following configuration of the control atoms. So they're both in the ground state here. then we say, well, nothing is happening to the target atom. So the target atom is always in the ground state. So this is how these are target atoms are initialized. So if both control atoms are in the ground state, nothing is happening. If one control atom is in the excited state, then the state of the target atom is rotated by some angle from the ground state to the excited state. And you see this brings some kind of superpositions into the game, which of course are absent in the classical process. But again, I mean, you see the connection to the classical process, to this infection process is direct, right? You see, there's a certain, when there's an infected site here, let's call this black or excited target atom infected, then you see there's a certain probability that this target atom here is actually infected as well. And you see very directly that this implements some kind of quantum version, as you wish, of this infection process, which is completely coherent. Yeah? So there's no rate equations at work. You see here, this is a perfect superposition of it's a perfect superposition state. There's no mixedness involved, and the whole I will show you in a second, the whole evolution that we are kind of implementing on this 1 + 1 dimensional lattice in itself is actually fully coherent. But you also see, I mean, this is not a complete fantasy. I mean, this is all these elements have actually been demonstrated already in the laboratory. So now we just need to find a brave experimentalist who really puts this in place and sees how well it goes in practice. Good. So this is the open quantum cellular automaton. This is kind of the theorist's version of it. It's exactly the same situation. You see here the two-dimensional lattice. You see here the direction which is time. You see here the direction which is space. And then you see here these gates that are applied always to 2 control atoms and 1 target atom. Then you apply the next gate to 2 control atoms, 1 target atom. And it's like in an old TV screen, you really scan this kind of lattice line by line in order to propagate now this initial state that is here prepared on the topmost time slice down to the future. So now let's do some math. Yeah, let's see how we can actually formalize this. And obviously you see this already here in the sketch and also in the previous pictures, that the fundamental operation here is executed by a 3-body quantum gate, as you wish, because it's an object that, or a gate that acts on 3 atoms simultaneously. And such a gate can be written down as this. And let me just go through through the notion here. You see, this is composed of 2 terms. And each of these 2 terms again is a product of 2 terms. Here P and U, and here Q and the identity. So this P and the Q operators, they act on the control qubit, and the U and this identity, they act on the target qubit. So now let's go through these operators. So you have this P operator, which is just an operator that checks if at least one of these control qubits or atoms is in the excited state, in the spin-up state. If so, then it applies the unitary to the target atom and it rotates it by an angle alpha. So it brings the state of the target qubit into a rotated state, which is parameterized by this angle alpha. And when the target qubit is in this pure state, the probability for being excited / infected / in the spin-up state is actually given by sine squared alpha over 2. So there we have a direct connection to the excitation probability. Then there's the other term here that checks if whether there's no atom in the infected or Rydberg state on the control sides. If there's no atom in these states, then nothing is happening on the target atom, and it remains in the healthy state or in the spin down state. And you see, this is how at the formal level we can implement this kind of gate which propagates our state through time. Okay, so just a comment here, and for this particular manifestation implementation, the order of the gates actually doesn't matter, so they commute. So whether I apply first G1, then G3, and then G2 doesn't matter. But this is just really a specialty of this very simple model that I'm discussing here. And of course, this can be changed, and we are currently investigating this. So now, obviously, we are not the first ones to investigate. You saw this also on the slide that I showed you a few minutes ago. We're not the first ones to investigate these cellular automaton dynamics. Maybe the first one to investigate this in this kind of quantum setting that I'm putting forward. But what's interesting to note is that there's a close resemblance between our construction and the so-called Domani-Kinzel cellular automata, which are actually, again, paradigmatic non-equilibrium systems that are kind of part of the standard curriculum that you will be exposed to once starting to learn about non-equilibrium statistical physics. And you see the resemblance is really close. Again, this is defined on this type of lattice that our quantum cellular automaton is living on. So you have a certain, if you have two target sites, control sites, out of which one is infected, then there's a certain probability P1 with which the target site is infected. And if both control sites are infected, then there's a certain probability P2 with which the target site is infected. But I want to emphasize that this is actually a classical process which is described by rate equations. And our system, on the other hand, is completely coherent. So you really, it's not either or. It's not a probability with which you are going from the healthy state to the excited state. You're really going into a superposition state here on the target side. So everything is fully coherent. But nevertheless, one can show that there's actually a mapping of this quantum process, again, which is fully coherent, to this classical process. And the interesting thing is now that this classical process has a phase transition, like the one that I showed you at the very beginning, where related this to the current pandemic. And you find here, again, the same phenomenology. You can take this now infection or flipping probability of a spin here. Just think of P1 equals P2 for the sake of simplicity. And then you see that, again, you find a situation where at long times you end up in a phase which is inactive, so all sites are healthy, or at long times you end up in a state where a finite fraction of sites is actually infected, and this is the so-called active phase. And you see this here very nicely. Just show you these space-time trajectories here in this inactive phase. If you start with a seed, then the seed will die out. In the supercritical phase here, the active phase, the seed will just proliferate and fill the entire system, infect everyone. And here at this critical point, you see the system doesn't quite know, do I want to be subcritical? Do I be supercritical? Do I want to be supercritical? And this gives rise to this interesting power law behavior and critical phenomena that one can typically observe in the vicinity of critical points. So also this quantum cellular automaton that is fully coherent, hence shows a phase transition. If one just runs the dynamics and asks what is the probability to or what is the density of excited sites here at the finite time slice, which is far, far in the future, so at long times. If you plot now the density of infected sites at long times, you also find that there's an active phase and there's an active phase, and in between you can switch by changing this rotation angle with which you rotate the target atoms from the ground state or from the spin down state to the excited state. So, but again, I mean, this is it's not like the pandemic. It's not a kind of probabilistic process with stochasticity involved. No, it's really a fully unitary dynamics. So this lattice here is in a pure state, because the only thing you do is you act with unitary gates. But what you want to analyze in the end is just this final time slice. And so to say, you are interested only in a reduced set of information. And this is leading you eventually to the emergence of this phase transition, because this fact that you only focus on a reduced set of degrees of freedom almost lets this dynamics look as if it was kind of an open system dynamics, because you're not interested in the full state, but only in a reduced subset of the information that is at your disposal. And this subset of information is, of course, not encoded in a pure state, but in a mixed state, which is represented by a density matrix, which you can actually also write down analytically. So this is super beautiful somehow, the construction. So it looks like a complicated two-dimensional quantum problem, but in the end, you can really write down more or less everything in an analytical fashion. And you can write down, for instance, this quantum state that you generate at this final time slice. And if you are a bit familiar with how to classify quantum states, you see immediately, well, I tell you, maybe you don't see it immediately because it's not clear what these coefficients are. I tell you, these coefficients are all positive here. These are actually can be interpreted as classical probabilities. And given that these numbers are all positive here, you see immediately that this is a separable state. So it is a quantum state, but it's, let's say, a boring quantum state, because there are no quantum correlations in the sense that there's no entanglement present by construction in such a state. These are details I skip over. So there's no entanglement present in this case, but nevertheless, this is not a classical state. And it's funny if one thinks somehow about what the notion correlation means, what is classical versus non-classical, one finds that entanglement is not the only thing that characterizes non-classicality. There are actually also quantum correlations that are weaker than entanglement, but nevertheless, they have no counterpart in the classical domain. And this is what you find here in the cellular automaton. And one such measure is the so-called local quantum uncertainty, which is related to so-called discord measures. If you have ever come across this, if you're interested in reading up, this is a work here by Gerardo Adesso, who is a colleague of mine working at the University of Nottingham. And this local quantum uncertainty, which is a measure that relates to quantum discord, is an object that actually quantifies the uncertainty that you get due to the non-commutativity between the observable, which is the density of excited sites, and the state, which in fact is not a diagonal state. It's a state which has also off-diagonal components in the density matrix. And this is not possible in the classical problems. So this is an actual quantum feature, and this measure that I'm going to apply now is one that quantifies this in the sense that it gives us a number and tells us, okay, this is how non-classical our system is. So this measure is calculated by some, and as it is always, if you're looking at these quantum information papers, they give you in the end some kind of strange object that you have to manipulate and for which you have to find eigenvalues or eigenvectors, and here it's exactly the same. So they say, well, calculate this object, which is a well-defined matrix that depends on the reduced two-spin density matrix of our state on the final time slice. And the nice thing again about this cellular automaton construction is that we can calculate this two-spin density matrix analytically. Yeah? So this is the structure. And you see there's one part here, which is, again, boring. It's just a direct product between a single spin density matrix and another single spin density matrix. But then there's here something that is not separable and describes correlations between the two spins. And the prefactor that is shown here depends on the density of the excited or infected sites minus the square root of the density correlation. So if these two spins are far away, we know that the density correlation function factorizes, and the square root of the square of the density is just the density itself, and this term would go away. So distant spins are not somehow in a state that is interesting. They are in the product state, but states they are sufficiently close, they will show interesting features. And another possibility for interesting features to be observed is a situation in which these density-density correlations extend over the entire system. And this is a situation which you typically encounter at phase transitions of the type that I showed you at the beginning, where you have this exponential behavior, for instance, of the order parameter as a function of time. The same algebraic behavior is also observable for these density-density correlations. So in the vicinity of phase transitions, we expect this correlation part to play a role. And indeed, one finds that if one now looks at these two-side density matrix and quantifies the density-density correlations first, then one sees these density-density correlations shoot up here at the critical point. Here's the inactive phase, here's the active phase. And you see here at the transition point, these things shoot up, which is not a surprise because, again, it's a continuous phase transition. And this is what one would expect, that, for instance, the susceptibility diverges in the vicinity of this phase transition point. But if you calculate now the quantum correlations by virtue of this connection that I showed you on the previous slide, you also see that these quantum correlations shoot up at the vicinity of this phase transition point, which I think is a very nice result. And as I said, it's almost obtained analytically. Of course, in the end, the precise values you have to compute, but at least you see that the two objects that determine these plots here are just the density and the density-density correlations, which you can extract from your simulations without problem. Good. So this is one step to introduce quantumness into the problem. But it's not, how can I say, giving rise to the most exciting insights, because in the end, it's just a rephrasing. Somehow it turns out this is all just a rephrasing of the classical process in some kind of quantum language. Of course, there's a bit more to it. It's not just a simple mapping, but by understanding the classical process, you can already understand a great deal of the corresponding quantum process. We want to make this a bit more complicated. We want to introduce correlations that are not these Discord type correlations, but we want to really introduce entanglement into the problem. And this is what I'm going to talk about now in the last few minutes, so that we also can come to an end soon. So how is this done? Well, let's go back to our fundamental gate, and I write it in a slightly different way here, which is perhaps, yeah, a bit more transparent than before. So what you can do is you can write this gate as the exponential of some operator, which depends on this rotation angle alpha. It just tells us what is the angle with which I rotate my healthy side towards an infected side. And then it depends here on two operators. First, this is this projection on atom 1, side 1 and side 2, just asking whether there is an infected site present or not. So if an infected site is present, then this projector gives us a 1, and then it tells us, well, rotate this side 3 here with this angle alpha. So this is what this gate does. And as I told you, it doesn't give us any quantum correlations that would give us a non-vanishing entanglement. But now what you can do is you can generalize this construction, and you can insert an operation which actually produces entanglement in the dynamics, and therefore really promotes now this non-equilibrium process one level up. Yeah, we already were quantum, we had coherences, we had Discord, but now we move one further step up and really introduce entanglement. And this is why I find this cellular automaton construction so nice. You can really have this kind of implement this hierarchical way in which you increase the amount of quantumness successively. And this is, so to say, the next level where this entanglement occurs. And this can be done by inserting some kind of unitary here in between. And okay, this details do not matter. So it's just a unitary that entangles spins. And this is parameterized by another angle, which we call little omega. So, and this plot is more interesting here. Now, when you want to understand how much entanglement is created here, actually, in the course of this applying this operation, what you can do is you can consider this setting of 5 sides, and you can ask, after the application of the gate, what is the entanglement that you can generate between these two target sites. Before, with the original version of the gate, the entanglement was 0. So these target sites are prepared in a separable state. But now, when you calculate an entanglement measure, which goes under the name concurrence, I mean, there are many entanglement measures out there, but this is kind of a nice one if you consider 2 spins. Then you see here that as a function of the entanglement parameter, you indeed see that entanglement occurs. I mean, it has kind of a funny structure here, which, to be honest, we haven't really looked in great detail, but the bottom line is that if you now move away from this omega equals 0, which is this original case where you have no entanglement here, this is this line, then you see, then you can introduce systematically in your non-equilibrium dynamics this kind of quantum entanglement, and you can ask yourself what is happening there. The problem now is that this whole situation becomes incredibly more difficult to study, because there's no longer a mapping possible to this classical Domani-Kinzel cellular automaton, and you are really ending up with having to deal with a 2-dimensional quantum state. And this is, of course, super expensive on computers. So the amount of resources that you need for this scales exponentially in the size of the system. And therefore, you have to think of a better way of how to encode this 2D state efficiently. And one way to do this, I don't have too much time to talk about this here, are so-called projected entangled pair states, which are a generalization of matrix product states into 2 dimensions. And on the classical computer, it's of course hard to do this, but it's doable. But the nice thing is, if you did do this in your Rydberg quantum simulator with a 2-dimensional lattice, you get such a correlated state for free, which you can then, of course, subsequently characterize by, for instance, measurements here at different points in space and time. And this is what I mean. You have now at your disposal the whole space-time correlation structure, and you can understand really the dynamics and the statics of your non-equilibrium process at once by just monitoring and studying this 2-dimensional state. Okay, I'm going to wrap this up. So this is the second to last slide. So just to show you, and let's say I have not an ultimate conclusion here on this, so this is still work in progress, but to really show you that this entanglement is changing something and makes life more difficult and makes definitely the state more difficult to represent on classical computers. Let me just show you this example. So let's look at this non-equilibrium dynamics now as a function of time. So this is the first time we are doing this explicitly, but okay, just to show you what we are doing here is we plot the density of excited or infected sites as a function of time. And we do this for different values of this gate rotation angle. You see, if the gate rotation angle alpha is below a critical value, then this density drops to 0. And at time going to infinity, you have no infected sites anymore. If the rotation angle is larger than the critical value, which we here set to 1, then you see you go to a state which is this active phase where the virus, let's say, becomes endemic. And then you have this kind of critical line in between where you have fine-tuned this dynamic such that your system cannot decide whether it wants to go to the state where everything is healthy or the state where you have a finite number of infected sites. So this is kind of the type of simulation that I showed you before that gives rise to some kind of finite that gives rise to some kind of non-equilibrium phase transition at long times. So now what you can do is you can now go away from this situation where there was no entanglement produced by the gates that you apply, which is this point here marked by the blue arrow. And you can now look at a situation where you basically scan different values of the entanglement parameter here marked by the red or the green and this orange arrow. And what you see is that, again, for choosing this entanglement parameter, which is this pi over 2, you don't expect entanglement. And in fact, it turns out that this dynamics is easy to simulate on the computer. But in between, at points where you create entanglement, you see that you have difficulties to encode the state within this two-dimensional projected entangled pair state. And also there are a lot of things to be said about this, a lot of details to be mentioned about this technique. But one figure of merit here is the so-called bond dimension of the projected entangled pair states, which is a measure of how many correlations you're allowing, you allow the state to represent. And what it turns out is that in these regions where entanglement is present, you need a substantially higher bond dimension in order to get this dynamics to converge. And you see directly the impact of the quantum correlations on the complexity of the dynamics. So this blue curve is for a low bond dimension, which is completely sufficient for this case and this case without entanglement. But you see it deviates now. If I compare this against the case with a larger bond dimension, you see these curves, especially for longer times, do not overlap, which is just signaling the role of quantum correlations, entanglement that becomes important here. Good. So final comment on this. You can, of course, now plot also the phase diagram as a function of this gate rotation angle and the entanglement parameter. It should be an omega down here. What you find is that indeed this critical line where the phase transition takes place shifts, but unfortunately the universality class is not changing, and I think now understood why that is. So we have another process, another way of putting quantum correlations into the system, and we hope that let's say in the next step of the study we are really getting a hold of well, this mechanism that creates these change of universality class that I talked about at the very beginning when looking at this quantum version of this epidemic spreading process. Good. Okay, this brings me to the end. Sorry, I've taken a bit longer than I should have taken. So that's why I make this short. I hope I could convince you that this quantum cellular automata are a convenient setting for exploring non-equilibrium physics. We can access space-time correlations on this two-dimensional quantum state, and we can introduce quantumness really nicely. We can interpolate between a classical limit and a full quantum limit, which features entanglement. And what is also interesting about this concept, that there's a direct connection to so-called feed-forward networks that are, of course, utilized heavily in machine learning applications. And one would wonder if one could also use the cellular automaton framework to, for instance, understand the impact and usefulness of quantum correlations in these feed-forward networks, neural network structures. There's a lot of other stuff we are doing. This is here in those papers if you're interested. Thank you very much for your time. I apologize for slightly talking longer than I should have. Okay.
Igor, thank you very much for this comprehensive, deep, and very intriguing talk. Thank you so much.
Thank you very much.
We can pass to questions. Please ask questions, sending us message through chat button, or you can also use microphone.
There are already a few questions here, so maybe I start with the. Shall I start with the first one, or do you want to moderate this?
No, please. Can you read these questions? Can you see?
Yeah. So one question is here: this connection between quantum cellular automata and measurement-induced entanglement transitions. Yeah. So yes, I mean definitely there's a connection. Just want to say here that we are not performing in this construction that are used in this work these measurements. Yeah, so it would correspond to a different class of cellular automaton dynamics, but definitely this entanglement transition you can study, and people have done this obviously in the context of the cellular automata, but it's not directly connected, I would say, to what I have been talking about. Okay. So yeah, cheers. And then there's another question. You said that there's no entanglement in the reduced state of each time slice. Yes, that is correct. Is there any temporal quantum correlations between the different time slices? Yes, indeed. I mean, okay, there must be, because let me just go back maybe to the presentation, because if there, just a second. This is somehow the interesting thing about this, yeah. So if there was no correlation between, let's say, the past and the present, then tracing out the past would just leave me again with the pure state here on the present time slice. So the fact that I have this kind of, yeah, you can even call it entanglement. I mean, this is what it is, right? So think of a Bell state of two spins. When you trace out one spin, you end up with a completely mixed state for the other. This is a direct consequence of the entanglement between those two subsystems. And this is exactly the same here. So if you, by tracing out this part of the lattice, you end up with a mixed state for this final time slice. And this is really a consequence of entanglement. Actually, we have a paper on this just recently put out on the archive if you are interested exactly on this kind of meta entanglement between present and past. This is this one. No, I had it somewhere. I find it. So if there are further questions, maybe you ask them, and then I try to find the reference to the paper. I think it was here. Yeah, this is this paper here. So this one down here, where we study this question. Good. Okay, there's more. Welcome. Okay, so
Igor, may
yes.
I ask one question?
Definitely.
So, innovative character of this research is obvious in many aspects. Can you please a little bit elaborate on application, technological application, or expected applications? All of
this I threw at you at the very end. Yeah. So as I said, so the let me just go here. If you think about neural networks, for instance, yeah, where basically the underlying structure of modern machine learning methods are layered networks, right? So where you have some kind of input here, and you propagate this input through layers to some output slice, and on this output slice you see the result, so to say, of the processing that takes place within your network. So that's why I'm saying that formally this quantum cellular automaton structure looks exactly identical to that. Yeah, and in fact there's also this work here by Torontegui and Garcia-Ripoll who look at kind of this question from directly this perspective. So they look at how you can connect an input slice to one target site, which would be a simple manifestation of a so-called perceptron. And now the nice thing about this cellular automaton construction is that you can just interpret it in a way as such a feed-forward network. You can implement now these quantum features, let's say, as I laid out by using these gates, and you can see whether, in some sense, yeah, the fact that you have now these quantum degrees of freedom allows you to, for instance, design algorithms. I mean, I'm saying something maybe stupid, yeah. Design algorithms that allow such network to maybe learn faster, or to have a high performance, even though the number of neurons is small. I don't know. I mean, this is what I would say could be a possible application of this this idea, this connection to feed-forward neural networks, which are undoubtedly utilized now in many applications. And yeah, I don't know whether this was too clear, but I hope at least just by looking at this picture, you see somehow the connection here to this quantum cellular automaton construction. Yeah.
So thank you. Other questions, please. Other questions, please. So if no other questions, Igor, thank you very much once again.
Thank you very much for having me.
We can close here. What do you think?
Sure, can do. Okay, and if there are questions, just don't hesitate to write me an email or so. Yeah, so I mean, don't be shy. I'm more than happy to discuss.
Sure. So the talk was, in my opinion, very deep and very comprehensive. It is very, very useful to our young researchers. And thank you very much that you say that they can write you an email, asking questions. Young people in general are shy here a little bit. But
well, the whole Zoom business doesn't help really, right? I mean,
so
it's
thank you
everywhere
for giving them this possibility.
Thank you very much for having me, and yes, have a nice evening and stay healthy. Bye bye.
Yeah, you too.